Next, let's take a look at the slightly more complex situation. It's a variation of the rig we have now. So let's open our file again. Under master geometry, we can see there are two models inside. Let's hide the original one and show the other one. Okay, now we can see it's a bit different from the original model. Originally, we just had a very simple sphere connecting to our base. Now our structure has become a bit more complex. We can see that our arrow model, it can only swing back and forth, because it's connected by a hinge here. If we want to swing left and right, we need to rely on this small part of our base and let it rotate like this to achieve that. So in this case, we need to do some relatively more complex setup in rigging, because from an animation perspective, the behavior I want to achieve is no different from before. I still use the same controller to drive this arrow model, making it point at my controller. The only difference is that during the actual rotation, I need these corresponding parts to only do what they are capable of doing. They can't do any weird movements that would break the structural connection between them. So how do we do this? First, we'll still follow the previous logic to rig this arrow. Then we'll see what problems actually occur. And once we find the problems, we'll figure out how to solve them. The method is the same as before. So here we create a few locators. We know its center should be in the middle of this small cylinder. So we create two and place them in their centers. Then similarly use a point constraint to find our actual position. This is our center point of rotation. And likewise, we have a center for up. So we do the same setup. Apply. This is no different from what we just did. We create a group, then make a parent constraint between them, and then put our corresponding two models inside as its children. Now look, when I move it, this model still follows along. But what's different is, as we mentioned just now, a sideways swing will break our original structural connection. What we need is, when it swings sideways, this model can rotate along with it to achieve this connected behavior. So here, let's think about how to achieve this behavior. First thing we need to do is separate our rotation axis. We know this object, our small arrow model, rotates back and forth. It actually also rotates left and right. It's just that when it rotates left and right, we need our base model to rotate along with it to keep the connection between them consistent. So our arrow model itself is moving normally in X, Y, and Z. But what we need is for our base model to follow along on the Z-axis rotation. But we must be careful here. It cannot rotate on other axes. It can't have this axis rotation. It can't have this axis rotation. It can only be Z-axis rotation. So how do we do this? Well, let's take a look at this. I'm going to isolate these three objects now. Our up locator. I'll scale it up a bit, and I'll give it a color, so you can see it better in my scene. Just look at our controller. When our controller moves, it generates rotation on all three axes to ensure our model always points at the controller itself. This is the definition of our aim constraint. But look, if I don't move my controller, which is our driver object, but instead move this up locator, what happens? No matter how I move this up locator, you'll find our model can only rotate on one axis. Why is that? If you recall the definition of the aim constraint and the mathematical formula we discussed later, it's actually quite easy to understand. Because using our model as an example, what is the first thing the aim constraint does? It makes our aim vector point 100% at our driver object. Then, what does our up object do? It's used to determine our second axis. What is the prerequisite for the second axis? The prerequisite is that the first axis always points to the driver object. So here, no matter how we move it, it can only change the other two axes. When we move it to this position, for example, you'll see only the direction of the Y and Z axis changed. The X axis, because it's our primary axis, will always point 100% to our driver object. So we can actually use this method to control this part of our base, because our base part only needs to rotate on this one axis. We just need to ensure its primary axis, which is the z-axis, is currently on, points perfectly forward. Then we use our second axis, say the y-axis, to control its horizontal rotation. Where does the second axis come from? It's actually the horizontal rotation angle of this yellow arrow itself. Where does this angle come from? We know it's always pointing at our controller. In this case, we can directly use our controller to do this. Okay, let's experiment. We create another locator. Let's rename it as well. We'll still call it aim pivot, but we'll add base to show it's for the base. Then let's isolate these two. Find its center point. Its center point is this point corresponding to the back here. So for this point, we can hold down V on the keyboard, then click the small circle in the middle and drag with the middle mouse button to snap it to this point. So now we've found this position. Here we need to use the up reference object we made in the previous step as the driver object for its aim constraint, and use our controller itself as its up reference object. So here, let's copy this name, then select these two to make an aim constraint. Here we'll stick with the defaults. If you don't want so many rotation values, you can analyze its current orientation. For example, z is facing forward now, so our aim vector should be z, 0, 0, 1. And the up vector should be minus y, so that's 0, negative 1, 0. Okay, so let's just stick with the default settings. So our driver object is the up reference object from earlier, this locator aim up 0, 0, 0, 1. And our up reference object has now become our controller itself. Let's do it. So now we have a new locator. We create a group just like before, still making a parent constraint. Then we put our two models in as its children. Now let's check the behavior. You'll see the relationship between them is now perfect. Look at this. No matter how we rotate it, the connection state between them will be perfect. Finally, let's do some cleanup. Put these three locators into a group called rig nodes. Place it under the master hierarchy as a child. Then we hide it. Just put these two into the corresponding model groups. Also, don't forget to delete the display layer we just created. Right-click on the display layer and select Delete Layer. With that, this slightly more complex, a variation of the aim constraint based on the original, is finished. A core rigging concept here is keeping the aim constraint's driver object position, while changing the up reference object to achieve rotation of the driven object on a single axis. By combining this method with our aim constraint method itself, we can achieve some, like the interlocking effect between different parts shown in our example, moving together. This rigging approach is very common in our work, especially when we are doing some relatively complex mechanical rigging. For example, a very common type like a robot. We know the robot's arms and legs. The interlocking of its parts actually follows a structure similar to this. For the animator, all they need to do is move a controller to, say, raise the arm or lower the arm. But for the rig, we have this structure in between. Behind this structure, we are actually using different aim constraints to drive it, so that even though the animator is just moving a simple controller, we achieve this interlocking effect between parts. I hope this section can provide some ideas in this regard. See you in the next video.